Thanks for joining everyone today. This is a joint webinar with the Adaptation Group of the North Central Climate Science Center and the Wind River Reservation Drought Project. This is Shannon McNeely, and today we are going to hear from Gabriel Senay on remote sensing-based actual evapotranspiration mapping for drought monitoring and water budget analysis. Gabriel is a research physical scientist with the USGS AEROS Center, but he is now co-located with us here in Fort Collins at the North Central Climate Science Center. His PhD is from Ohio State University. His research focuses on satellite-derived evapotranspiration modeling, and he has a broader interest in regional water budget studies for drought monitoring and early warning applications in the U.S. and across the globe. So with that, I will turn it over to Gabriel to get started.
All right. Thank you, Shannon. And thank you, everyone, for joining. So I will be giving an overview of the work I do in the use of satellite data for estimating evapotranspiration, mainly for drought early warning, monitoring and early warning and water budget analysis. I guess I have to explain myself a little bit why I'm here and my connection with AEROS. As you can see, the AEROS mission is providing science and imagery to better understand the Earth. And if you look at the Climate Science Center mission area, it's also very comparable to provide scientific information, tools, and techniques to anticipate, monitor, and adapt to climate change. So where do I find myself in these three circles? I use hydroclimatic data to monitor this circle vegetation conditions, and also look at irrigated fields. So I think I find myself somewhere really at the intersection of all three circles. At least what I think, that's what I think where I belong. There are teams and the contributors from USGS, AEROS, and also government and non-government employees. So a lot of graphics. I get help from AEROS employees. So we'll talk about a little bit of give you a summary, some background and justification why we use remotely sensed data. And I will show you examples using the MODIS data and the Landsat data and some future work and some conclusions. I'd like to show a summary in case some people are in a hurry to leave, but I hope nobody's going to leave. But the main thing is satellite-based ET is being estimated operationally using the land surface temperature. All the work I'm going to show is based on the land surface temperature as the main driver. The product I'm going to show you for drought monitoring is reliable as is, the product. I will show you examples. But if somebody wants to use this evapotranspiration data for water budget studies, it requires calibration because satellite data is consistent, but it may have bias. That's why ground truthing is very important. We're going to talk about evapotranspiration as part of the hydrologic cycle. As you can see in here, the precipitation comes here, and the evapotranspiration returns it back. Also, stream flow takes it away to streams and lakes. The focus in here is evapotranspiration. What is evapotranspiration? Well, this is a gaseous component of the water budget. When we look at water budget, which is the rainfall, stream flow, and evapotranspiration. So the other ones are liquid form, whether it's in solid form in some kind of ice or snow. So it's gaseous state and invisible, and it's very difficult to measure directly. So all the methods you see evapotranspiration in indirect measurements. The process of evapotranspiration is there are two sub-processes. One is transpiration, which is when water is drawn through the root system, goes through the plant, and then out through the leaves, through the stomata. So that's the transpiration component. But the evaporation, that's just water being lost from the surface of the soil or from the surface of the leaves, not necessarily going through the plant. But it's very difficult to differentiate the two. There are methods of differentiating, but for a lot of us, our interest is the combined water loss. So we combine it and we call it evapotranspiration. Why do we look at ET? Why is this important for us? The first thing is it's a response variable. as opposed to precipitation, which is the driver, which means, the vegetation, the landscape is responding in the use of water. And this response reflects the integrated effects of energy and aerodynamics, soil moisture conditions, vegetation type and condition, and environmental stress like salinity. So if we break them into two, there is a potential, which is how much energy we get from the sun, whether it's cloudy or not, and how much is the humidity in the air, and how much is the wind. So this doesn't require any presence of water in the environment. So this is just a potential. That's why it's a climate variable. When people talk about potentiality, it's a climatic variable, which is the interaction of radiation and the atmosphere. But when you bring in limitations, which means is there moisture on the ground? If there is moisture on the ground, the potential will be realized. But that's not enough. Is there a vegetation at a healthy vegetation condition? If the healthy vegetation condition is available, this potentiality will be realized. But how about is there stress in the environment? Is there salinity a problem? Or there is land degradation stuff? But if that's an optimum condition, again, the potential will be realized. So all these factors are limiting factors that reduce the amount of water that goes into the atmosphere. So with this brief background, the EROS Water Smart or Water Census project is a USGS-funded project. We have been tasked the last 3 years to develop improved ET models for crop consumptive use and apply the models nationally. There are two scales I'm working on. One is what's called a landscape, a field scale, where water use is required, which means we want to know how much water and where is water being used in the field. These different plots you see are colors indicate the amount of water used by the different fields. This is a result and remote sensing ET from somebody else, from David Eckhart. When you are interested in really individual water use, but how about what we're interested in is just simply a water budget, which means how much of the rainfall that comes in a given basin is lost in the form of ET. In that case, we don't need to know really the individual fields water use. All we need to know is how much water is within the basin. For that, we can use a coarser data set like MODIS. For this, we have to use something like Landsat. I will talk about special details later on. So what is the role of remote sensing in here? Well, remote sensing is a data source. So we get data to model ET. As I said earlier, one importance for ET modeling is land surface temperature. So if you're interested in field scale, as I showed you earlier, you want to use Landsat. That's what we have, about 100 meters for the thermal. MODIS gives you about 1 kilometer, AVHR is 1 kilometer. Then the geostationary satellite is a 10 kilometer, but a higher temporal frequency. There are other models that, use a water balance approach. Then ET is driven by precipitation, and there are other sources like the NOAA NextRad 5 kilometer daily, Meteosat satellite data 10 kilometer, NASA TRIM. These are all rainfall products. But the one I'm going to show is all focused on Landsat and MODIS using land surface temperature. There are two basic principles of ET estimation. The first is a water balance, which means we account for precipitation, how much rainfall comes into the landscape, and how much of it is returning as a form of ET through some water balance accounting methodology. It has its own limitations. So now, today I'll talk about energy balance, which means now, evaporation of water requires water that you can do it through water balance, but evaporating water takes a lot of energy. So we can also solve this problem by accounting the energy that came into the system, and that's what's lost for evapotranspiration. There are different models for this, from soil moisture, from vegetation index, from surface energy balance. Even within surface energy balance, there are CBAL metrics. There's so many models available. And we have simplified surface energy balance. The OP stands for operational. The thing is, which models to use? Well, wise notes from a statistician says all models are wrong, but some are useful. So it means we have to choose a model that we are comfortable and the one that meets our objectives. Most models will give comparable results generally. I'm not going to talk about the water balance-based ET estimation, but I just will point out the limitation of using that, so why we are using the energy balance. So water balance, which is tracking the rainfall, which means you need good rainfall data. We need to characterize how the vegetation is using water, and we need to know the kind of soils available. That's not really a problem in the U.S. There is good rainfall data, there's good information on soils. But the most difficult even in the U.S. is we don't know, especially in irrigated areas, how much the farmer is applying water to the field. If we don't know that information, we cannot solve the ET. And also the contribution of subsurface extraction by deep-rooted plants. If we don't have that information, we cannot solve it. Also, the impact of pest and disease has to be incorporated in the model if you want to estimate ET through a water balance approach. The one I'm talking about, the energy balance, incorporates all of this. It will solve this. It's thermal-based, so which means the temperature of the land will give us a lot more information. So I'll talk about the details on the model later on. So the energy balance approach, so I'm going to talk about, we use the model for water use and availability assessment, but also for drought monitoring. I will show examples for each case. This is a schematic of the model. So I can explain this. Probably 50% of the model is really in here. So the left schematic shows you the data source to the model. So which means the data source, non-remote sensing data, we use weather data, standard weather data, radiation, temperature, wind, relative humidity, pressure. That gives us the potential or the reference ET that I said when water is not limiting. It means how much the atmosphere demands water from the landscape. But the landscape is limited by water. So for that, we use land surface temperature that is derived from satellite data. We use air temperature for parameterization. So at this point, let's say from land surface temperature, we'll get an ET fraction that may vary from 0 to 1. What's it going to do is it's going to correct for non-potential conditions. This potential condition is the ideal plant supplied with a lot of water, unlimited water. There are no pests or diseases or no salinity, no environmental stress. But if there are any stress that comes from water, lack of water, from pests, disease, or salinity, this ET fraction will handle it. So at the end, we'll get an actual ET. So how does land surface temperature vary in space? This is the right schematic will help. A hot and bare and dry pixel, when it will be very hot to a touch. So this would be the hot pixel we will experience if we go out in the field. On the other side, a well-watered, healthy vegetation will be cooler to the touch. The difference in temperature in the cold surface of this vegetation and the bare ground could be as high as 40 degrees Fahrenheit. So which means really walking barefoot on a bare ground in the summer, July day, you will feel really a 40-degree difference from the air. So that's really the main driving factor. So this equation that goes into this, I'm not going to go into the details, but the energy balance approach says this is a net radiation, incoming, outgoing radiation. So once you have that useful energy to do some work, that energy is available to do three things. One is the latent heat flux, which is it could be used to change the state of water from liquid to gas, which is evapotranspiration. It could do that. Or that energy can be used as latent, sensible heat, which is to heat up the air. So that energy is available. Or part of the energy could be just energy that goes into the ground. So these are the three components what is available. So usually a lot of energy balance calculation, what they do is first they solve the sensible heat flux, which is relatively easier to calculate, and we can assume a daily value amount of G is 0, and then if you know the net radiation, and then you can solve ET as a residual. So we don't do that. In this simplified approach, we'll just do a direct approach of solving ET instead of sensible heat flux. So just without going too much detail, I have a schematic that will help explain this a little bit better. Again, this is the last graphics I have in explaining the model, maybe the other 50%. I'll show you an example. So this is July 4th, just an image from MODIS. So I'm showing you a transect from New Mexico to Oklahoma, from New Mexico to all the way to Oklahoma. And there are 3 lines in here. And this is the profile showing elevation, mountains in New Mexico and, plains in Oklahoma, eastern Oklahoma. And the 3 lines, the first line is air temperature data. As you can imagine, the mountain is cooler, and it increases and much higher in the plains. All right, so that's how you feel the air temperature. And we have found a way of calculating DT. DT is really a difference between, I told you, the air temperature and the surface temperature if you touch it. So if the air temperature is this, what we're saying is there's a bare ground in Oklahoma. It would be, the air temperature would be, some 40 degree Fahrenheit higher. Okay, so now we have the 2 boundaries. The air temperature is here, then the surface temperature is going to be here for a bare ground. Now what you see in the middle line is the land surface temperature you get from the satellite data. When you look at it, the land surface temperature is not as smooth as the air temperature. It's, goes up and down. As you would expect in the mountains, it's kind of cooler. And then it goes up, generally stays up, just goes up and down, almost erratic. Now let's look at 2 points. Let's look at 2 points. This point in here in eastern Oklahoma and the one in New Mexico. They have the same land surface temperature from this line, right? Around whatever, 313 or something Kelvin. But they have the same surface temperature for a different reason. Otherwise, it would have been easier. If it's surface temperature, change it to ET. We cannot do that because they have the same surface temperature for a different reason. Why? And here, let's say this is closer to the air temperature, right? Okay, so I'll just assume because I told you air temperature is cooler than the surface, so it's cooler. So this guy is also, but when the same surface temperature, but way farther from its air temperature. So it's closer to the bare surface temperature. So whenever the surface temperature is closer to the air temperature, what we are saying is actually there is no energy transfer because when temperature is about the same, there is no heat transfer. So if there is no heat transfer, it must be there's energy changing. Maybe there's a change of state. So which means the water, when the water evaporates, there is no change in temperature, but there is a change in state. So from liquid to gas, that uses a lot of energy. You know what that does? That cools down the surface. So that's really the main principle. So if you look at a fraction, it varies from 0 to 1, or in this case, for ET fraction 1 to 0. What we are saying is, if the surface temperature is closer to air temperature, its ET fraction will be close to 1, which means the plant it will evapotranspire at a potential rate. That's what we're saying. But for this point, the surface temperature is closer to the bare surface temperature. So which means it's not as evapotranspiring as much. If it was closer here, it would have been transpiring as much. So which means this is a dry environment, whereas this is more vegetatory environment. So that's the main principle. From this on, I think it's all about showing you how the data is and then some products. So where do we get the data? As I showed you, land surface temperature from the Landsat, 100 meters or MODIS. Air temperature we use for parameterization, like lower boundary, upper boundary conditions. So we use DAMIT, PRISM, WorldClim for global application. The potential condition comes from also NLDAS, which is North American Land Data Assimilation System. We can also use station-based evapotranspiration data, but these are for potential conditions. A little bit more about the satellite data. This is a schematic for a MODIS, a Terra satellite, where the MODIS sensor is located. There are 4 other sensors. These are the description of the satellite. So as the satellite passes over, it's a polar orbiting around the poles, and it takes image. Pass time around 10:30 equatorial time for Terra, and there's one in the afternoon, Aqua. But it's collected, and the MODIS satellite has got 36 bands. What it means, we collect data in the blue, green, red, the one we know is the optical bands, but also the ones we don't see in the near infrared. even more, there's a thermal, which is really emissivity of the land. The land emits based on its temperature. So all this, out of all these 36 bands, for this product I'm showing you, we are using this band, and it's a thermal band, where we get land surface temperature. The data is available in something like this for the globe. This is, for example, an 8-day average land surface temperature. As you can imagine, vegetated in mountain areas will be cooler, whereas the southwestern U.S. and the Sahara will be warmer. So, and the other important product is the potential ET, which is the Penman-Montes equation, which is really driven by net radiation and aerodynamic factors or the advection, about humidity and stuff. And this is a standard equation, and we solve this 6 hourly from NOAA data, and for the globe, the data is available at the AEROS website. So how does the model perform? As I showed you earlier, this is the air temperature kind of boundary conditions throughout the month from January to December. As you would expect, January is cooler, and June, July is hotter, air temperature. But, but also the surface temperature, remember, if it is completely bare, surface temperature would be higher. So you can see this big difference in June, July. So what happens to land surface temperature? Land surface temperature got closer to the bare area, which means really dry air environment. Whereas in this month, for example, in August, the land surface temperature was closer to the air. I mean, there is some moisture provided from rainfall activity. So we convert that into ET fraction, and then finally ET. What you see is a comparison between the model ET and flex tower ET from AD covariance. So in Arizona, actually, a tough environment model, so there was good correspondence. And a similar approach in Oklahoma, again, which year is this? That's 2005. Same thing, air temperature, land surface temperature, and we don't expect an exact match on this station. Then this is the modest pixel 1 kilometer. So, but I think generally we're capturing the seasonal variability, the magnitude also reasonable. Another comparison we did was with my postdoc. We compared mod 16 ET from Montana. This is our model, and this is the gridded FlexNet from Max Planck Institute in Germany. What you see is the water balance ET. What it means is you can estimate ET based on the difference between precipitation and discharge. So from USGS, as you would expect, there is a lot more ET in the southeast where there's a lot more rainfall and vegetation. But this doesn't really capture irrigated areas because it doesn't have information about irrigation. When you look at our ET in Central Valley and the Snake River Basin, anything in the yellowish and greenish indicates a lot more ET. So there is a lot more spatial detail at 1 kilometer. This is a gridded FlexNet. Its course is 50 kilometers. You can see also it misses out, but generally there is good comparison space. With modest ET also very comparable. I think in this case, our model did a little bit better in the southwest in capturing irrigated areas. So I'm just now showing you a lot of products. How we use ET now. Okay, this is ET. This season. How did the season do? How is the season working? This is the previous year, for example, ET anomaly seasonal. What you see in the brown red color is drought conditions, which means the ET was much lower than the average condition, whereas it was much better or performing above average for the northern plains. And the drought monitor kind of corresponds generally, but remember there is a time mismatch. This is a weekly product, whereas this is a seasonal product. These are the different years again. You can see the 2012 drought, widespread drought, and the focused drought in 2011, Oklahoma and Texas. So there is a lot of confidence that we're getting the drought monitoring well with this. If you look at the ET in depth and absolute magnitude, this is how it looks for the different years, green being higher, but anomalies are easier to explain. Again, the anomalies come out, the droughts in 2002, 2006, widespread drought from north to south in the middle, and the California drought in 2007, even 8, also 9. I think they got a break in 2010, and then 11, then it came in 12 and 13. So again, more comparison with drought monitor. Remember, these products are automated pretty much, every 8 days we generate this and it gets posted on the website. whereas this product requires a lot of intervention, a lot of people, experts. We got also funding from USAID. Now we also do global modeling of droughts. And again, brown is drought. You can see 2012 when it's drought in the U.S. There are also droughts in part of Europe and Asia, and even Brazil. There was some drought. So now I'm going to show you a close-up to Colorado. Okay, so here in Colorado, green areas is higher ET. This is for 2014, last year. And you can see the spatial detail in ET. You don't find in precipitation, because ET is not only precipitation but also vegetation cover as well. You can see higher ET part of the mountains, as you see in Boulder, Eastern, Loveland, Fort Collins. Generally, there is more ET activity. Some of it comes from irrigation, but wherever there is a stream flow, you can see by following stream there is a lot more ET. It makes sense along the riparian areas, so moisture is not limiting. And when you compare to land cover, this is ET I showed you earlier, and you can see some areas. I was surprised by this. I think I haven't been to this area. You can see in between mountains, probably rainfall is not as much. The true color picture shows you there is not much vegetation. Greener is vegetation, but also ET. You see the ET is much lower. In terms of drought anomaly for Colorado, last year was above average condition ET in the north, but below average condition in the southeast.
Southwest.
And southwest, yeah. But now I'm going to show you more years. So really bad in 2000, really bad 2002. It's amazing. You can see even drought years, though, it's part of the mountains, they don't seem to be affected because maybe they get enough moisture, to meet the physiological needs of the plants. And then a good year was 2004. Well, not everywhere though. At least almost there is somewhere in every year there is some drought affecting. And 2006 was bad in the northeast, but not the rest. And 2011 the southeast was bad. In 2008 and 2009 was good. And look at 2012, it's really one of the worst. But you can still see part of the mountain. There is still, grays about, so there is enough moisture. So drought could be very spatially, freaky. So 2014, even 2014, so good in the north, but south, that's what we talked about earlier.
Aren't some of those alpine areas though? What does it do at the high?
In here, where is it just
what does it do at the high alpine areas where there's no trees? Wouldn't that be?
Probably what it does is year to year it behaves similarly, so it would be gray, which means there is no year-to-year variability.
Right.
Yeah, when you see a lot of deep red and greenish, which means these are really the ones that change from year to year that much. Mm-hmm. Yeah, if it is always dry and stuff, it will be just normal condition, yeah, because it's just simply an anomaly. Yeah, yeah, that's a good point. Now, for Shannon. So, yeah. And the rest of you, I can take it. So just a close-up of ET in the Wind River Basin is just from 2013 using Landsat 8. Green areas is higher ET following river corridors and on the mountain sides where there is vegetation.
What's the time period of that?
2013 from April to, I think I had May to September. It's just a seasonal total. Mm-hmm. So what you see in here is a true color. So what shows you, the true color shows you where there is vegetation. If it's green, there is vegetation. So then what am I bringing with this image? This is just tell you how much water that plot of land used. So there is the volume of water used. So the ET is really how much water this area has used. So this tells you where the vegetation is how much water. As you would expect, the greener it is, it's going to use more water. So generally around the lake area, there is a lot more irrigation probably going on. There is a lot more ET.
So is there no coverage on that eastern boundary of the where it goes outside?
Yeah, no, they're just the one.
It's just not the one you chose.
Yeah, yeah.
Gotcha.
It was part of already the image we processed, so we didn't. It was outside of the Colorado River Basin. We didn't. So it's.
But we can get that.
Oh, of course.
Yeah.
It's just a satellite swap. So
right.
Yeah.
Right.
Yeah. So now I'm going to show a close-up of this in terms of drought, just the way I showed you for Colorado. So this was 2000. As you can see, this is a lot of irrigation is inside here. Not everywhere is irrigated. So you can see, that if it's irrigated, it becomes gray because, it's getting its water, or this color, maybe it's, 20% lower, 30% lower in worse years. So if you look at even the bad year 2001, again, you see around irrigated areas, and here is where irrigation is. It's not as bad as in these areas. Of course, this is not irrigated. So you can see the year-to-year variable. 2004 was good. 2006 was a drought. Again, there is some reduction. There are some irrigated areas in Central Valley. You don't see any change from year to year. Even if it's a drought year, they have enough water to meet their irrigation demand. Toward a Wind River, they get affected. If it's a drought, they don't have enough water necessarily, so there might be curtailment. So that would be another thing to look at, really, how is really the drought affecting the irrigation system as well. Again, this is just above normal. Even when it's above normal condition in other areas, but this is an irrigated area, so it doesn't get too excited even in Goodyear because it was getting its water anyways. So, but non-irrigated areas they tend to fluctuate to bad and good, whereas irrigated areas are more buffered.
So 2013 is relative to 2012.
In 2013, you just want to compare the two?
Yeah. So what we're looking at in 2013 is the change from 2012.
No. What you see in here is the change from the average of the last.
From the average.
The average of the last 14 years.
14 years.
Yeah.
Okay.
Yeah. It's compared to the last 14.
Okay.
Yeah.
Why 14 years?
Because that's the data we have for MODIS.
Gotcha.
Yeah. Right. So seems like both of them were not as good. Were not good.
No, they were not.
Yeah. So 2013, but for 12 was more widespread, but 13 was also. But again, 14 came out better. But from 2009, it was really good. So, well, I didn't know I have more. This is just to show you more, just how we use Landsat and.
Keep going.
When we process Landsat, for example, for the Colorado River Basin, these are the different paths we need to process. And there are about 43 Landsat path rows, and for each path row, maybe you want to get 15 images, 9 to 15 images, depending on cloud cover. So it's just processing Landsat is a lot of work, but now we are working with Google Earth Engine, which will speed up the processing. So how does it look, MODIS versus Landsat at really large scale? They look very comparable. What you would expect they will happen. Now I'm going to show you the close-up. So this is Landsat, of course, true color, false color imagery, and this is MODIS, but this is how it looks in Landsat. Landsat is much resolution data compared to MODIS. So you can see in here the irrigated fields here. In Landsat, you can see each one of them, and then within the field as well, the variations. So if you are really looking at water rights, individual fields, Landsat is the way to go. But again, basin scale, you can see this MODIS and Landsat more spatial detail, and there's a base map. And in Landsat, you can see the center pivots in here. But if you average all this, you're going to get comparable results. So your basin scale analysis. I just want to show you a spot in the upper Colorado River Basin. These are irrigated fields. Again, this is just an image, and that image taken one time, but this is a seasonal value. So what I want to show you is, this is, for example, a center pivot, or no, not necessarily center pivot, irrigated field, and then I want to show you how it looks like when you look at season within a season. So a center pivot or irrigated field will have, of course, lower ET in January, February, because energy is also limiting, and higher ET or higher water use will be in June, July, as expected. But for the whole basin in here, if you average it, of course, it will be much lower because there are non-irrigated areas within the basin. Now I'm going to show you just in southern Colorado, and I think in another irrigated areas, basin. And you can see generally these are, again, seasonal totals. We match most of them, but there is no necessarily one-to-one correspondence between the two. When you look at the ET of the center pivot pixel in here, it's much higher. It gets in July, much higher ET, and this is a whole basin average ET. So the whole thing I'm showing you here is also you can get the seasonal dynamics of evapotranspiration water use. We can do even golf courses. There was a challenge, and people want to see, and whether we can detect ET by golf courses, and this is a base map, and this is ET estimated from land surface temperature. So we can even look at ET water use by golf courses. Next step, if we have time, is to differentiate the private versus public courses, because the shape files are labeled, so we can look at water being abused or managed better in different sectors. So, just really, I'm just show more graphics if you have time. If you look at Las Vegas in here, this is Lake Mead, and you can see some higher values. Maybe some of them are golf courses. Again, I want to stress the spatial detail you can get from remotely sensitive data, especially Landsat. So, with the few minutes I have, I just want to talk about a couple of slides on delineating reservoir surface area from satellite imagery using historical data. Again, the principle is straightforward. When you look at, for example, a Landsat surface area, water looks completely different from the background soil and vegetation, so it's easier to map surface area for water body. Now the question is, how do you estimate historical water level? Well, each surface area can be tagged to a certain elevation in the landscape, so by associating it with the topography or bathymetry map. An example would be, say this Landsat imagery, when it's full, this is a certain cross-section in Lake Mead, and it could represent, the wider extent of Lake Mead surface area. If Lake Mead dries down during dry times, the surface area shrinks, it will be smaller, and it will be tied to this elevation. So you can associate a certain surface area to a certain elevation. Then you can reconstruct the historical, pretty much hydrograph of the river or the lake. Just while I'm at it, I just want to point out, actually there is a lake altimeter data by NASA, which measures the major lakes like Powell and Lake Mead and stuff, and globally.
So can you go back to your previous slide? Can you convert it to volumetric?
Yes.
Yeah. Okay.
Yeah. Once you have the surface area and once you know the elevation difference, you can calculate the volume straightforward. Okay. Just the rest is really straightforward calculation. Yeah. Exactly. All you need is area and depth. So this altimeter data is available globally, but the reason I brought this up is if you have altimeter data, it's good, but it's only available for major lakes, not for the Wind River Reservoir, for example. It's only for major lakes of the world. But this data is very valuable data is available, and for example, it shows, for Lake Powell, it's, now it's at this point, it's online, you can go and check. It has been going down for last many years. There is a data gap for some reason in Lake Powell during the JSON satellite, but this data is available for most of it. And we applied it, postdoc applied it, use Landsat. We reconnaissance using Landsat surface area. We compared to the altimeter data, and we calibrated the Landsat surface area elevation. We estimated Landsat-based surface area, converted to Lake altimeter, and compared to the altimeter data that's generated by NASA, looked good. And then what we did was, altimeter data was not available prior to 1993, so we used this Landsat satellite data. We reconstruct the history of lake level and lake Turkana. So we can do the same thing for other lakes in here using Landsat. So, in conclusion, I guess I want to say we can monitor landscape response anomalies every 1 square kilometer. That's what I showed you using MODIS. That's straightforward for drought early warning, and we want more people to use it. We can map and quantitate crop water use in volumes. That's what I showed you as well, for irrigation districts like center pivots and stuff. But I always warn, careful ground truthing of remote sensing data is important for bias removal. It's consistent data. It's good for anomalies, but if you want to use it for volumetric estimation, you need to remove a bias. Sometimes a 5% bias could be a huge amount of water. It could really, bring a lot of troubles especially in the western U.S. where water is so precious. So that's all I have. So,
great.
if you have any questions, happy.
Thank you.
Sure.
So I'll start just by talking a little bit about, it seems to me that these are some pretty potentially powerful tools for a project like the Wind River project, working with the managers, looking at historical and seasonal water use.
Right.
And so I know you said you've used this for like famine early warning systems. Right. How would you sort of envision working with the scientific team and with the tribal managers to do actual drought monitoring for them in sort of real time, so to speak, on say an irrigation season time scale, for example?
Yeah, I think the MODIS data, the one I showed you even for the Wind River, it's updated every 8 days.
It's what? Updated every day?
Every 8 days.
8 days.
Every 8 days. It's on the website. But the website's graphics, so we can share the data if people want to manipulate. So looking at how from April on until October we post the data. So people start looking from April on, from April 1st. Every 8 days they can come to the website and look at the graphics. Is this above normal, near normal, or is this just way below normal? So the data is available. Will help them start assessing. Okay, this is overall drought in the region, which might affect our crop performance in the future, because some of the ET they need from their crops may come from rainfall, right? So that the regional drought will affect the amount of water they need to apply on the irrigation. So I think the point I want to say is the data is available if they want to monitor, and if they know. Now the question is if they know the drought like by May in relation to other year. What kind of decision they make. I'm sure they know what to do with it, but the data is available that will tell them how severe it is, how widespread it is. So we can share the data for them. The next step would be maybe forecasting it to the end of the season. That's possible to do. It's not available now, but by May, for example, we say, well, the ET is really 10% below normal. But assuming the rainfall would be an average condition, you can forecast it. So what would be the condition by August? That's possible to do. But again, this is based on average climatology forecast. So as you get closer, you get better and better because most of the data is based on observation. But we don't incorporate forecast weather data. I mean, that comes from, we don't do that. So this is really a monitoring product. I believe in a good monitoring product is really helpful for early warning and preparedness. By mid-season, you know how your crops are going to perform. So, so I guess the point is the data is available, and we'll be happy to share the data.
Add maybe a question is what capacity the given manager, water manager, or crew would have. What tools are they currently using, and maybe we think about how we might integrate into their existing tools, so they don't have to reinvent or redo a tool. For example, if somebody's using ArcGIS, could we put on a server somewhere? I know we've done this with Phenology or other MODIS products, a tool to see those data right within ArcGIS, so you don't have to go to a different website. So I think that something to think about for Wind River or other locations is what that person is currently using to make their decisions, and can we bring this into that system?
And so we've been working with them to create these climate and drought summaries. The decision two-pager that I sent you, the first one was just released last week, working with the High Plains Regional Climate Center and the National Drought Mitigation Center. And so I could see this folding into that and bringing some additional imagery and narrative that we can include in that summary. Did anyone else on the phone have any questions or comments? I know, are Jennifer and Cody still on? Did either of you have any thoughts about that?
A question. I wondered if it's possible to differentiate between the different types of vegetation, so you could see corn versus alfalfa versus wheat or forest.
This method just, it gives you an average. It doesn't, the good thing is the method doesn't require information about the plant type to give you an estimate of ET. So what we do is, if you are interested to summarize the ET by vegetation type, what we do is we combine it with land cover data. I think USDA has the land cover data called CDL, where they publish whether it's field is alfalfa or corn, soybean. So what we do is we summarize the ET by those land cover maps. So it is possible to do, but we don't do that part. But the data is available that can be used to summarize our ET or drought anomalies by cover type.
Gabriel, thank you for the presentation. This is Imtiaz. So I assume that the data is archived as daily values?
As 8-day values.
It's 8 days, not daily. But even then, I think it's the time frequency is high enough to kind of do what I would imagine a short-term risk of drought and other extremes that relates to that. And I'm thinking here the issue related to heat waves and fire weather and the value of this product for those kind of issues.
Yeah, actually, we were asked 2011 to do flash drought mapping. That's how it's, and I think I collaborated with Mark Soboka on that as well. So that's how, and the land surface temperature is so sensitive to the heat wave. It was more sensitive than the NDVI-based index because just sensitive to moisture and stuff like that. So you are right. I think it's possible to do this. We just need to monitor it and plot it and compare it to observe it, heat wave impacts. And if somebody has good data, we can go back in retrospective and analyze this.
So, but how does the issue related to bias affect those things? I mean, I saw some of your slides where when you compared it to the flux network, the biases were very small, it appeared. And so how big is this issue and how does it affect, our understanding of these mechanisms related to drought and other extremes?
The biases would not affect if you are interested in relative changes like for heat wave and this flash drought. The biases will affect because it remains consistent just from year to year. The biases will affect for people who want to plug this in the regional water balance, water budget analysis. So they want to compare it to the precipitation, how much precipitation is, and how much was the discharge. Oh, does it add up? We just need to add up to the precipitation, to the source. So that's the only impact it has. Otherwise, in terms of detecting changes, anomalies, it will not have any difference.
Right. So what are the other issues you feel that needs still to be resolved or with this product?
Well, again, one thing we wanted, like for the higher resolution for Landsat-based data, we have the temporal frequency problem. Landsat comes every 16 days, and you have a cloud problem, and then it becomes, every 2 months sometimes. So really, if you have money to launch another Landsat, then that would be it, So the frequency issue is a problem for Landsat-based, but for modest-based coverage, I think the product is ready to be used for a lot more applications. It's not being used, actually.
Right. Thank you.
Sure. You're welcome.
Anybody else? Questions, comments?
Just a note on the crop types is there's a latency of the last year, but the National Ag Stats, NASS, whatever that does produce a crop type map. It would be a year old. Right. But you would have that at a Landsat scale. through USDA.
Yeah, true. And anyways, most of our products will have also a year latency, you know.
So assuming there's not much land cover change in that year.
Yeah,
and you know, it's not a safe assumption with corn and soybeans. You know, crop types, they can change. You know, so you would, you know, you'd have at least last year's, and we could do some analysis to overlay those crop types with the previous years.
Well, and for areas like Wind River and a lot of areas in Colorado, they're doing ranching products anyways, so it's hay and alfalfa that doesn't really change from year to year anyways. So
yeah, and you could make that assumption. Look at the last 10 years; it hasn't changed.
Right.
Okay,
yeah.
This is going to be hay.
So I heard that somebody produced a modest-based climatology land cover. They looked at areas that don't change that much. They created a climatology land cover.
There's relatively little food crops in that area, so.
But yeah, the latency is a problem, but you know, depending on kind of the level of detail.
So I had a question about the reservoir mapping work, but I want to give, if anybody else has any questions or comments, I want to give other people the opportunity first.
Yeah, I'm going to jump in just with a quick question. With the anomalies, clearly, you know, your hands are tied with how much data you have. You have 10 years or 13 years or whatever. But I wonder if you've thought about or run into issues where you might need to sort of contextualize the anomalies in another way. So you might say, oh, well, we know all those 10 years were dry years or wet years. So a drought within a series of dry years or a series of wet years is very different. Some parts of the world, maybe that's an issue. Like the Sahel, they have these long-term dry and wet cycles. I don't know, and it seems like maybe it's a good opportunity to bring in local knowledge and say, well, we know these last 10 years have all been dry.
Right,
so
exactly.
Even though it looks a little wetter in 2002, that was still really bad for us, right? You know.
Yeah, if you bring in longer-term variability.
That's a good point too. But even that, when I look at that graphics, you know, some areas are very flaky. They change from year to year because those are maybe the sensitive areas. Whereas the other ones that they change slowly because they have really a good, you know, modulation in the system. So you can interpret the anomalies in many ways.
That's a good point. Anyone else on the phone have any questions, comments? So I'll jump in then. We had talked about doing this reservoir mapping kind of analysis, and it's something that there's a real lack of data in some of the reservoirs at Wind River. And so what would that entail? Because you said that would actually probably require some additional funding to do that. So
well, requires one dedicated graduate student. I'm interested in it because I'm also, you know, looking at that area as part of some of the funding work, but I don't know when the timing is, but it's really getting some person spending time looking at Landsat data over time.
So it'd be like a full-time grad student type thing?
It doesn't have to be, really. It doesn't have to be full-time. Maybe grad student full-time, grad student working half-time. Is that what you mean? Yeah.
Would it require additional funding for any other support or data access or anything like that?
No, those are all easily, freely available data.
Okay.
So, the task is straightforward, to be honest.
And how far back could you reconstruct?
1980s.
1980s?
That's with Landsat, you know, Landsat 4 in 84. And Landsat 5, I don't know, 84, but since 84 I know there's Landsat 5, so.
And then can you do projections based on that as well, using climate scenarios, or?
That would be another component. It has to be combined with, you know, understanding the dynamics. It gives you a historical context, and if you know that, and somebody tells you climate projection. So, I know the climate projection maybe, you know, you guys are. But
Joe and MTIAS, working with Joe and MTIAS, that might be something.
That would be something, you know, combining, understanding. The first thing is to understand that, you know, historical dynamics and how that's related to the climate. So what we are looking at, the hydrology, you know, how it's variable. Most likely it's tied to the snowpack. Of course, you know, there's irrigation water use aspect to it, but, you know, the supply comes from the snowpack and other reasons. And if somebody says, well, the project climate is above normal, you know that it's going to affect the reservoir. So. But at least we can give you the historical context, especially when you say that that reservoir doesn't have a gauge. I think it's ungauged reservoir. So this would be a way of really getting data about the operation of the reservoir.
And do you need reservoir bathymetry? You need the...
Yeah, I think it should be available.
Or is it available?
It depends. They're different. Did you want to talk about the Stakeholder Advisory Group real quick?
If I could just add a sentence to let this group know, and thanks for this talk. It was neat to see the interaction between the three circles, probably brought to life with this. But just a heads up that the North Central is doing a joint stakeholder group with the USDA hub.
Stakeholder Advisory Group.
And USDA doesn't like to call it advisory. They call it the Joint Stakeholder Committee.
Okay, but just so people know what we're talking about.
So replacing our Stakeholder Advisory Committee with a Joint Stakeholder Committee between the USDA and the DOI North Central. We sent out invitations on that roster. We're hearing back from most people. I think there's 2 or 3 that I was like, okay, we're assuming if we don't hear back from you, we're done, or you're too busy.
And then you told me Gary Collins is going to be on that, right?
Yes.
Okay.
He did agree to be on it.
From Wind River.
From Wind River, and just to think about how can the adaptation group maybe take more advantage of or look to that group as this is our social network of trusted people who are willing to engage. I think that we haven't really explored how the adaptation team could say, okay, we've got a group of stakeholders, and these are invested people. So
stakeholders meaning they're largely agency and tribal representatives, Department of Interior,
multiple agencies,
Park Service,
EPA, USDA,
BLM.
Quite a few agencies, Bureau of Rec, Corps of Engineers, a handful of USDA agencies. So maybe we can think interviews to these people, or kind of understand what their concerns are. Try to get a little bit better grasp of what they're after in their agency through the expertise the adaptation group brings to the table. So it's just something I think we kind of had a stakeholder group because we had to have one. It was set up before we started, and it just kind of rolled along. And I thought, well, this is maybe a time to take a fresh look at that group and see how it can better use it. And then the adaptation group has grown quite a bit.
Yeah, I think it'd be great to do interviews with all those folks.
That's like something.
Yeah.
I don't know how that would unfold or what we'd ask them.
Yeah.
Obviously, that's the devil a little bit in the details, but we have a group of people who are willing to sort of work with us.
Yeah.
So let's maybe take
totally. That'd be fun, actually.
Yeah.
Great. All right. Thanks. So I'd like to thank you, Gabriel, for that talk. And is anyone still on? Did anyone else have anything to chime in at this point before we wrap it up? Oops. All right. Well, thanks, everyone. Have a great weekend. This will be recorded.
Thank you, Gabriel.
Oh, you're welcome.
Okay, bye-bye.
It will be recorded and available on the website, so if you want to refer back to it or send it to anybody else.
Excellent.
All right. Thanks, everybody. Bye-bye.